Okay, good morning and welcome to this video course on advanced hydrology. In the last class we looked at the derivation of expression for terminal velocity of a raindrop falling through the atmosphere, okay, in which we balance the three predominant forces which act on such a case. Okay. Then we looked at a couple of data representation methods, that is rainfall heatograph and the rainfall mass curve. Then we looked at the procedure of developing what is called a maximum depth duration curve, and associated with that we also saw how we can develop the maximum intensity duration curve. Then we went ahead and looked at one numerical example of calculating the duration intensity, the maximum depth duration curve and the maximum intensity duration curve given the data about a particular rainstorm. After looking at that, we started looking at what is called the IDF relationships or the intensity duration frequency relationships, in which we add another dimension which is called the frequency of occurrence, and this frequency of occurrence we measure in terms of the return period. Okay. We say that the higher the return period, lesser is the frequency, right. A 100-year event would occur less frequently as compared to a 10-year event, all right. Accordingly, the magnitude of a lesser frequent event will be more severe or higher. That is to say, if you have a 100-year event, its flood magnitude would be much higher as compared to the magnitude of a 10-year event. Okay. So, we see that the frequency of occurrence also has a bearing on the magnitude of particular rainfall or flood or any hydrologic variable. So, that is why it was important to add this frequency dimension into our analysis. Okay. So, then what we did is we looked at this IDF relationships. Okay. If you go here, we plotted a few maximum depth duration curves, all right, and the maximum intensity duration curves, and then we said that India Meteorological Department or IMD has come up with a relationship after studying a lot of data, rainfall data of different durations and frequencies in different parts of India. Okay. And they came up with this relationship in which we said the I is equal to k T to the power x divided by d plus a to the power n. Okay. In this I we said is the intensity of rainfall in centimeters per hour, capital T is the return period in years, and capital D is the duration in hours. Okay. And these four parameters k, x, a and n, these are called the parameters of this particular model, and these have been estimated or calculated by IMD, and these are available in your Subramania's book. Okay. So, I suggest that you have a look at these values of k, x, a and n, and once we have that for a particular region, all we need to know is what is the duration in which we are interested and what is the frequency of occurrence or the return period T in years, and then we can find out what will be the worst case scenario as far as the intensity is concerned. So, these intensities can be used in hydrologic design. What we will do today is we will start with another similar concept which is called aerial averaging of the rainfall. Okay. Remember, in the beginning of this course we had looked at the classification of the hydrologic models, in which we said that the hydrologic models can be either lumped or distributed. All right. What was the difference in a lumped model and a distributed model? Well, in a distributed model we account for the variation in the hydrologic variables with respect to space, and in a lumped model we ignore those variations with respect to space, right. So, what we then need in a lumped model is the single value of rainfall. Let us say if we are doing rainfall runoff modeling, then you need the average rainfall in a very large catchment, and you may have 2 or more rainfall gauges in a particular catchment. So, we need to calculate the average rainfall over the space. Okay. So, what we will do is we will look at 2-3 different methods and their relative importance, all right, and applicability criteria about calculating the average rainfall. Okay. So, we will get started with the new topic today, which is called the average aerial rainfall. Okay. And in this as we said there are many methods, and we will look at them one by one, and the first one of them is the most simple method. It is called the arithmetic average method. Okay. So, in all of these methods, what we are going to assume is, let us say that this is your catchment, you may have a river running through it, these are different branches and the flow is taking place from right to the left, and then let us say you have, these are the locations of the rain gauges, okay, and there may be many different rain gauges depending upon the density of the rain gauges in that particular area. So, in the arithmetic average method, all we do is we just take a simple average, that is your p bar is nothing but 1 over n summation of p I goes from 1 to capital N. Does that make sense? It is a simple average or arithmetic average of all the data in terms of p I, where p I is, needless to say, is the rainfall which is recorded at ith rain gauge in the catchment. Okay. And clearly capital N is the total number of rain gauges in the catchment. Okay. So, if there are n number of catchments, n number of rain gauges in a catchment, then all we need to do is just take the data on a particular day or particular time period which is recorded at those different rain gauges in the catchment, and just take the average of them. All right. So, that will give you the average rainfall or the spatial average rainfall in that whole catchment, which can be used in rainfall runoff modeling or any other purposes. Well, the simpler the method, less useful it is, okay, and this method is hardly used, although it is very simple, but it is almost useless and it is not very popularly used at all. This method is rarely used, in fact, in practice. Okay. Why? Because it's not able to account for the amount of rainfall, the area each rain gauge represents, and so on. All right, it's just simple average without accounting for many of the factors which are important. All right. Well, then what do we do? There are some more methods which people have developed. Okay, and one of the most famous method which you may have seen earlier is called the Thiessen polygon method. Okay. So, the second method which we will see quickly is called Thiessen polygon method. Okay. As the name suggests, we try to do some kind of construction in the form of polygons around a particular rain gauge in a catchment, and then we say that that particular rain gauge is represented by the area which it represents. Okay. And how do we draw these Thiessen polygons? Well, there is a well defined procedure. Before I go to that, this method follows certain assumptions or certain principles. All right. Can you tell me what are those? I am sure you have studied this in your undergraduate classes, right. So, what are the assumptions or what are the basic principles on which it is based? All right. So, let us look at that first. Okay. All right. This method assumes that, okay, number 1, at any point in a catchment, the rainfall is same as that at the nearest rain gauge. Okay. What does that mean? That means the rainfall in a catchment at any point in the catchment is same as the rainfall at the nearest rain gauge. All right. So, whatever is the value of the rainfall at a particular rain gauge, the area which is surrounded which surrounds this particular rain gauge, we say that it is the same rainfall in that whole area. Okay. So, that is number 1. The second one is that the depth or the rainfall depth, that is recorded at a given rain gauge or given rain gauge is applied out to a distance halfway to the next station. In any direction. Okay. So, what does that assumption mean, or what does that principle mean? That if you have 2 rain gauges and if you join those 2 rain gauges by a line, all right, then the depth recorded at one particular rain gauge is applied up to the middle of that line or the midpoint up to that line. All right. After that point, the another rainfall which has been observed at the next rain gauge station is what is assumed in that particular area. Okay. That is why we do this midpoint bisectors, and then that is how we develop these Thiessen polygons. We will see in a minute. All right. Well, then let me try to show you how we do these Thiessen polygons. I am sure you may have seen earlier. I will not draw the river geometry here. So, what we do is we just join the locations of the rain gauges by straight lines such that they form triangles. Okay. The first step is I am taking only 3 rain gauges here for the simplicity for demonstration purposes, but there can be many number of rain gauges in a catchment here. Okay. So, whatever it is, then what you do is you join them in such a manner that they form triangles. Okay. Then what we do is we draw what is called the perpendicular bisectors on these lines. All right. We draw the perpendicular bisectors. All right. So, you take the midpoint, all right, and draw the perpendiculars on them, that is your perpendicular bisector, right. So, it is this line, it will be this line and it will be like this line. Okay. Does not show exactly like that, but you understand what I mean. All right. Then this whole area is represented by this rain gauge. Let us say this is 1, this is rain gauge 2 and this is rain gauge 3. So, this is your area, we call it A1, we call this area A2 and we call this area A3 and so on. How many areas will be there? As many number of rain gauges which are present in the catchment, right. So, what we do is we divide the whole catchment area into n different number of Thiessen polygons, okay, which will be equal to the number of rain gauges. Once we have done that, then what we do is we assign a weightage to each rainfall observation in the ratio or the proportion of the area it represents with respect to the total area. Okay. So, then your P bar will be equal to 1 over A summation of your A I P I, where I varies from 1 to capital N. Let me see if I put the value. Yeah, I did. Okay. Okay. So, here what is A I? A I is nothing but the area which is represented by the ith polygon or the ith rain gauge, okay, where and other things are same. Actually, the P I is the rainfall recorded at the ith polygon or rain gauge or in the polygon, where capital A is nothing but summation of your all the AIs, I varying from 1 to capital N, all right, total catchment area. And P bar, of course, I think we did not define it earlier, so we can do that now, is the average aerial rainfall in catchment. Okay. So, you see that in the arithmetic average earlier we saw that the weightage assigned to each observation was same, all right, it was 1 by n, all right. So, you have P I by n plus P I by P 1 by n plus P 2 by n plus P 3 by n and so on. Here what is the weightage? If you see this formula above, your weightage to the ith rain gauge is nothing but you can see A I over capital A, all right. So, it is in the proportion of the area which is represented by that catchment. Okay. All right. So, this is a method which does account for the area which is represented by the particular rain gauge, all right. It is much better than using the simple average, and this method is quite popularly used. However, this also suffers from certain weaknesses or disadvantages, this method. Okay. What are those? Let us look at them. We will write these down. What are the disadvantages of this method? Okay. So, the first one is that this method is not flexible. Flexibility is very important, as a new Thiessen network must be constructed each time there is a change in the gauge network. It should be very clear to understand. You see that these Thiessen polygons are constructed depending upon the locations of these rain gauges which are scattered throughout the basin or a catchment, all right. If for some reason one of the rain gauges is defunct or is not operating, and it has to be replaced by some other rain gauge nearby or something, or a new rain gauge is to be added, then this whole Thiessen polygon construction has to be done again. Okay. So, it is not flexible, which takes some time, all right. Number 2, this method, or it does not account for orographic influences on rainfall. What do we mean by that? If you have a very large catchment, all right, one of the rain gauges may be close to the mountains or the hills, all right, the rainfall patterns will be quite different there due to the orographic patterns as compared to the plains, all right. So, this method is not able to account for the orographic influences on the rainfall when we are doing the averaging only with respect to the area it represents or represented by the Thiessen polygon. Third one is the effect of rainfall magnitude itself. Rainfall magnitude itself is not taken into consideration. Okay. What do we mean by that? Different rain gauges which are scattered in a catchment would observe different amount of rainfall, and there may be a pattern. All right. In a large catchment, one geographical local location may be prone to high amount of rainfall consistently, and the other one small amount of rainfall. If that is the case, and if you are using Thiessen polygon, then one of the rain gauge which has higher rainfall will not be adequately represented, because its weightage is always same or in the proportion of the area, okay, which may not represent the proper importance in calculating the average. So, somehow being able to account for the magnitude of the rainfall also in addition to the area a rain gauge represents is also important. Okay. So, what we do is we have another method which takes care of some of these weaknesses, or which overcomes some of these limitations, and then we call that what is called a iso-Heitel method. Okay. So, the third method we will look at is called iso-Heitel method. Which overcomes these difficulties or these limitations. Now, what is this iso-Heitel method? I am sure again that you may have seen this in your earlier classes, right. What is an iso-height? Well, an iso-height is a line joining in a catchment which represent equal amount of rainfalls, all right. Like isobars are the lines joining equal amount of pressure, isotherms are the lines joining in an area which have equal temperature. So, similarly, an iso-height is a line or curve joining all the points which represent or which have the same amount of rainfall. Okay. So, this is a very important concept. What we do is we construct the iso-heights in a catchment using the rainfall magnitudes which are observed at a particular rain gauge station. All right. Okay. So, let me give you this method and then we will look at it. So, what we do is iso-heights are constructed using the observed depths at the rain gauges, and then they are interpolated between adjacent gauges if that is required. Okay. So, what we are doing basically is that we are using the rainfall observation magnitudes at the rainfall locations or rain gauge locations, and then developing contours. All right. This is similar to your contours which may have contouring which you may have done in your survey classes earlier. Okay. So, you have these benchmarks as the rainfall depths scattered around the basin, and then what you do is you can develop these contours of iso-heights. Okay. There are software available these days to do this. So, you can use a software in which you can delineate your catchment, you can put the locations of the rain gauges and put the benchmarks at the as the rainfall magnitudes, okay. And then it will give you the contours or the iso-heights at some desired contour interval. Okay. So, I will not go into the details of that. Then what we do is the area AI between each pair of iso-heights within the catchment is measured or computed. Okay. Again you have the two iso-heights, all right. In between the area is let us say A, all right. You can either measure it using planimeter if you are working manually on a map, or if you are working on a software, it will automatically give you the area between two iso-heights and the drainage boundaries or the catchment boundaries. Okay. Then let how we define is the Pi is then the average rainfall depth Pi is the average rainfall depth of the two boundaries boundary isoheights. Is calculated. Okay. It is not the overall average rainfall. This is Pi. What is Pi? Pi is the average rainfall in an area which is bounded by two isoheights. Okay. We will look at it graphically in a second. Okay. And then the same equation which we had written earlier for Thiessen polygon is used. The same equation is used to estimate P bar. Okay. So, if we look at this catchment where you may have these three different rain gauges in which the rainfall values, let us say maybe one on a particular day, or this may be the normal rainfalls. It may be, let us say 3, and let us say it is 5 or something. I am trying to be very simple here, as you can see. So, between these two rain gauges, all right, you can select, let us say 2 centimeters, all right, something like this. Between 3 and 5, you may want to have a contour corresponding to 4. Okay. So, this line represents 4 centimeter, this line represents, let us say 2 centimeters. Okay. So, this way you can have many number of rain gauges in this catchment, and then you can draw these isoheights which may have very complicated shapes. There may be circles, there may be ovals, and so on. Okay. So, just for demonstration purposes you have this, all right. Here the rainfall may be very minimal or close to 0 or whatever. So, if you look at this one, let us say this is Pi minus 1 or not Pi minus 1, this is your I minus 1, the isoheight, and this is your ith isoheight, and let us say this is Pi, or this area is Ai, all right. So, the area which is bounded by the two isoheights having 2 centimeters of rainfall and 4 centimeters of rainfall, that is your general ith area, all right. So, Ai is the area between two isoheights, which one? Which represent the rainfall Pi minus 1 and Pi, all right. And then you say the Pi actually is the average of these two. So, you have Pi minus 1 plus Pi. So, you are overwriting this Pi divided by 2. Okay. So, this is the rainfall in this catchment, okay, which is the average of these two values. So, which is 3 centimeters. Okay. So, you keep on doing that for all the areas, and then you finally use the same equation. The overall average is nothing but summation of your Pi Ai over total A, where I varies from 1 to capital N, where capital N is the number of areas which you have, or inter isoheightal areas. Okay, that is what it is called. So, you see that this method, the isoheightal method, is the most accurate method. Okay. Why it is most accurate method is that it is accounting for the areas which is represented, or the area which is represented by a particular rain gauge location, number 1, and also it does take into account the amount of rainfall that occurs or that falls on that particular rain gauge, all right. So, it will be able to take care of the orographic influences and any other pattern in the rainfall spatial variation in the rainfall. Okay. So, this way you will have a better estimate of the average rainfall. Okay. So, this was the third method of aerial averaging of the rainfall, and the last one we are going to look at quickly is called the reciprocal distance squared method. This method is not very common in India actually. This is used mainly in the United States, in which what they do is the effect of rainfall on a gauge point or at a location on any other point in the catchment is assumed to be inversely proportional to the square, as the name of the method suggests, to the square of the distance between the two points. All right. So, the rainfall on one gauge point and the rainfall on another gauge point. All right. How are they related? Well, you take the distance between the two, and the rainfall we say is the inversely proportional to the square of the distance between those 2 points. All right. So, it should be very easy to compute also, as you can see that if you have two locations, let us say one is x having coordinates x1 y1 for example, you have another point let me call it x1 and x2, another point has the coordinates x2 y2, then you can easily calculate the distance between the two locations x1 and x2, which would be x1 minus x2 whole squared from the knowledge of your basic geometry. All right. And then the weightage as per this method is what? 1 over this distance square. All right, reciprocal distance square method. Once we have the weightages, then all we need to do is it will be summation of your Pi Wi I varying from 1 to capital N divided by summation of W or the total W's. The summation of all the weights should be then equal to 1. Okay. All right. So, these are the 4 different methods of calculating or estimating the spatial average rainfall in a large catchment. Okay. Now, what we will do is we will look at something extremely important in this chapter, in which we will try to calculate the intensity of rainfall coming out of a thunderstorm cell. All right. So, I will go back to the PG book, in which we will look at what is called a thunderstorm cell model. Okay. Okay. So, what is a thunderstorm? First we will look at what do we actually mean by what is a thunderstorm. It is basically a convective cell rainfall, or there is a convective cell or thunderstorm cell that gets set up in atmosphere during certain conditions. All right. And the rainfall that is coming out of that thunderstorm cell is due to the convective processes. Okay. So, what happens is we will look at a thunderstorm cell first, and then we will go to the equations. What is it? It is nothing but a vertical column of atmosphere. All right, and it is made up of 3 parts. Okay. So, what I will do is we will look at the diagram first, and then we will come back to the equations. Okay. Okay. So, what it is this is a cylinder, vertical cylinder. All right. The portion in the middle you see is a vertical cylinder, and then there is a vast expanse on the upper side which is the into the clouds, and one is close to the bottom or the ground. All right. So, what we have here is, you see here, this is the ground at the ground level. Okay. The air gets into this thunderstorm cell close to the ground inside it. Okay. Then it gets lifted, as we had seen earlier that there is one important basic physical mechanism for rainfall to occur is that the air mass needs to get lifted, and in this particular case it is a convective or a thunderstorm cell. So, air mass is getting lifted in this middle region. So, what we have is this of height delta Z1, this is called the inflow region, and I will come to that in a second. The air, the moist air enters into this thunderstorm cell through this inflow region. It rises in the middle, all right, and then what comes out from here on either side, all right. This is of height, let us say delta Z2. Okay. So, the air, the dry air comes out from what is called is the outflow region, all right. This is of height delta Z2. Okay. So, what we can do is we can take a cylinder of actually some diameter d, right, okay, and then ultimately what we are interested in is we want to find out the rate of rainfall or intensity of rainfall that will come out of it or that will be observed on the ground, all right. So, you have the precipitation intensity I, okay, which is observed on the ground, all right. All right. So, let me quickly write down the three parts or the three regions, which is one of them is the inflow region, okay. As we have seen, it is near the ground, all right, where the warm and moist air is drawn into this thunderstorm cell, okay, from the bottom. Then the second portion is the middle portion, which is called the uplift region, which is called the uplift region. It is in the middle, all right, where the moisture condenses as the air rises. Okay. Remember, we had said that for rainfall to occur, it needs to rise so that it can condense. That condensation takes place in this middle or the uplift region, producing rainfall or precipitation. Okay. And then you have the third region, which is the called the outflow region on the top. Okay. Is the upper part or the upper atmosphere where the outflow of the cooler and drier. Okay. So, the moisture has been taken out of it, air, the outflow occurs. Okay. So, this way we see that in a thunderstorm cell it consists of these three parts, all right. And what we will do next is we will look at how we can use our Reynolds transport theorem and apply these equations to this. Okay, so, we see that in the thunderstorm cell there are three regions. The warm and air, the moist air enters at the bottom close to the ground through the inflow region. It gets uplifted in the middle region and then it comes out and the water condenses and comes out as some certain intensity, and the dry air and cooler air comes out from the top from the outflow region, all right. The air that comes out from the top, all right, can descend down, all right, at the outside, all right. It can pick up some more moisture and re-enter into this thunderstorm cell, all right, and then this process can actually get set up, all right. This is called the convective cell circulation or the convective cell pattern, which is responsible for rainfall intensity I coming out, all right. So, what we will do is we will look at this mechanism, all right. Basically, what we are saying is that the outside the cell column, what I just said, the outflow air which has come out from the outflow region may descend over a wide area, pick up more moisture, and re-enter into the cell. Okay, at the bottom or close to the ground. This entire pattern, all right, is called convective cell circulation. Which is driven by the vast amount of heat energy which is released by the condensing moisture. As the condensation takes place, there is a lot of heat that is released from this physical reaction. Okay. Moisture in the, where is this heat? In the middle portion or in the uplift region. Okay. All right. So, this is what is called the convective cell circulation, and this outflow region can be as high as about 8 kilometers or 16 kilometers into the atmosphere. That is the maximum height of your convective cell circulation clouds. Okay. Now, a thunderstorm cell, what we will do is, may be visualized as a CV or a control volume, okay, and we apply our Reynolds transport theorem to it, okay, to see how the movement of the moisture is taking place and how we can calculate the rate of rainfall that is coming out of it. Okay. All right. So, what we will do is we will write the continuity equation for the moisture or the water vapor in the thunderstorm cell, all right, and we have already mentioned what is the control volume. It is a cylinder of diameter d. Okay. All right. So, what we have actually is we have already seen that capital B is equal to your m, beta was q v for this case, all right, sorry, now beta was not q v, beta was m v dot we assumed, all right, and then we have already written at the beginning of this chapter that the continuity equation for the moisture, all right, in the mixture of air is m v dot is equal to the first term over the control volume of what? It is going to be equal to, I am sorry, let me go back and correct this, that is actually your q v, I was right, and then beta rho d v, okay. That is the time rate of change of extensive property stored within the control volume, all right. And the second term is the control surface of your q v, rho a and v dot d a. Okay. Now, let me first define that you have an inflow region and an outflow region. So, let me say that the inflow region is cross section 1 and the outflow region is cross section 2, and if we define all the properties, the climatic conditions at 1 or the inflow region, let us say the pressure is P1, the velocity of the winds there is V1, all right, the density of air is rho 1, all right, then you have QV1, all right, is the relative humidity there, the temperature is T1, all right. Similarly, the other quantities at 2 is with subscript 2. So, you have P2, V2, rho 2, QV2 and T2, etc. So, everything is defined with subscripts 1 and 2. Okay. All right. Let me go back and number this equation as 3, 3, 5. Okay. That is the numbering scheme we have been following. All right. So, let us work on what will be this term mv dot. Okay. mv dot is what? Physically, what does it represent? It represents the time rate of change of mass. All right. How is the mass changing? Is the mass being created or destroyed within the control volume? All right, or it is changing in different form. So, we see that although the mass is not being created or destroyed, but it is changing its form from vapor to liquid, and that liquid is coming down as certain intensity I. All right. So, if you want to write down the expression for m dot V, what would it be? Okay. Now, let us assume that the precipitation intensity is I, okay, and let us say it is in centimeters per hour or some other suitable units. It is falling over a cross sectional area of that cylinder which we have seen is, let us say, is equal to A. All right. So, with these notations, what will be the mass flow rate of water leaving the cell, and let us say the unit of that is mass, let us say is kilograms per second, all right, will be equal to what? That is what is your mv dot, that is what we want to find out, okay, is equal to, if you see, it will be rho w I A, should be easy to see that. Let me write the units in the brackets. Rho w is the density of water, which is kg per meter cubed, times I, let us say, is in meters per second, area is, let us say, square meters. All right. So, you have meter cube cancelling with this, what is remaining is your kg per second. Okay. So, rho w I A represents nothing but your mv dot, all right, and we are going to put a negative sign in front just to be correct as far as the notations are concerned. Now, let us assume that the flow is steady state. Okay. This convective cell circulation which we are assuming and the rainfall intensity I coming out, let us say that all of this process is steady. Okay. Under that assumption, the first term will be equal to 0, all right, in your Reynolds transport theorem or this equation 335. So, this quantity will be 0. So, if you want to write this down, you will have negative rho w I A, that is your mv dot, left hand side, is equal to the first term is 0 and the second term, let us break it into two parts. Okay. So, you have the, for the outflow region, you will have q v rho A v dot d A term plus over the inflow region, what is the q v rho A and v dot d A. Okay. Let me say that this is my equation 336. Okay. So, all we have done is we have said that because of the steady state nature of the flow, first term is 0, mv dot we have said is rho w I A, and on the right hand side the second term in the Reynolds transport theorem we have broken into two parts, outflow region and inflow region separately. Okay. Okay, now, we have already defined that there are various parameters. So, what we will be able to do then is we will write these terms in terms of those parameters 1 and 2. Okay. So, if you did that, you will be able to see that rho w I a, I am taking negative on the other side, will be equal to q v rho a v, all right, all of these things at subscript 1 or the inflow region, all right, times the area, all right, area through which the things are entering. So, if you look at from the top, it is a circle of diameter d and height is delta z, all right. So, what is the area? All right, the perimeter is the pi d and the height is delta z1. Okay. So, it is, let us say the area is going to be pi d delta z1. Let me go back to some of you, here it is. Okay. So, this is diameter d, all right, at the bottom things are entering into a height of delta z1. You see that this is your delta z1. Okay. And it is a diameter of or it is a circle of diameter. Okay. So, it is going to be the area is pi d delta z1. Similarly, then you have the inflow which is negative, you have q v rho a v at cross section 2 times your pi d delta z2, all right. So, let me number this equation then as 337. So, this is the equation that gives me the relationship between various parameters, the specific humidity, the density of the air, the velocity, the diameter and the intensity and so on. Okay. What is my objective at this point of time? My objective is to determine this guy, this I. Okay. Rho w I know, area I know, and on the right hand side I know everything close to the ground. Okay. Close to the ground I can measure various parameters, the pressure, the temperature, the humidity and so on. But what I do not know is this quantity q v rho a v at height 2, all right, at the outflow region. So, what I do is I actually need one more equation which can relate these quantities at cross section 2 or the outflow region. Okay. So, what I can do that is I can write the continuity equation for the dry air. Right now, I have written the continuity equation for the moisture in the moist air. Okay. So, what we do next is we write the continuity equation for dry air. Okay. That will relate this quantity with the other quantities. Okay. And why we are doing it? To find q v rho a v at 2 as a function of other known things. Okay. All right. So, for the dry air where the flowing fluid is dry, let us say your capital B is the mass of the dry air. Okay. So, what will be beta? Beta will be dB over dm, which will be the mass of the dry air per unit mass of the flowing fluid which is dry air. So, it will be 1. Okay. So, dB by dm will be equal to 1. Also, assume a steady state process, all right. So, if we do that, then what we will have is your continuity equation left hand side is 0, all right, will be equal to, because there is nothing coming out of the dry air, as the dry air is moving, there is no moisture exchange that is taking place, all right. So, this left hand side is 0. The first term on the right hand side is also 0, and then you will have the over the cross section or the control surface of your rho d, your v dot dA. So, this is my 338. Okay. This rho d I will say is rho a times 1 minus q v, all right. We put into this equation, what I will have is 0 equal to rho A, and then I expand it 1 minus q v of your v delta z, all of these quantities at 2 times pi d. So, I am opening out the v dot d A term like I did earlier, minus you have rho A 1 minus q v of your v delta z, this quantity at 2 times of your pi d. Okay. I would like to draw your attention and see if these things make sense to you or not. All we are doing is rho d we are replacing by this quantity, and you are expanding your v dot d A term like we did earlier. Okay. So, this will actually give you rho A v delta z at cross section 2 in terms of other known quantities. Rho A v delta z at cross section 1 times 1 minus q v 1 divided by 1 minus q v 2. Okay. So, this is an important relation you get by applying the continuity equation to the dry air in this case, all right, and let me number this as 339. Okay. Now, what I can do is we can put this rho A v delta z at cross section 2 back into your equation or the continuity equation for the moisture. Okay. That way, or let me write it down, substituting 339 this equation which you have just seen into 337. All right. What is 337? It is this one, okay. All right. And then we take area as, let us say, pi by 4 d square. It is a circle or cylinder of diameter d, and then simplifying what we can get is this expression for I, which will be 4 rho A 1 v 1 delta z 1 over rho w d times your q v 1 minus q v 2. You should be able to see that. You can verify this 1 minus q v 2. This is your final expression.